free-falling objects. So when an object falls just without any interference, we call that a free-falling object, falling towards the ground. Not falling up, but falling towards the ground. Okay? And it has an acceleration that has been studied and verified and proven, and it is 9.81 meters per second squared in a perfect world. In your notes it says ignoring resistance of air. In a perfect world, if there was no friction, no resistance of airflow, none of those things, acceleration would be 9.81 meters per second squared. Okay? Acceleration due to gravity, so we've learned this, that acceleration is represented by the letter A. And we'll see that as we go further. We'll see A, C, and all these other different A's, except for gravity. Gravity gets its very own letter. It's a lucky duck. Okay? It gets a G. And so 9.81 is the average value on Earth. If you were on Mars, you would have a different acceleration. If you're on Jupiter, yet again different. And even on Pluto, who's no longer a planet but is kind of a planet, you yet again would have a different G. Okay, acceleration is different planet to planet out in space. There is actually, contrary to popular belief, there is gravity in outer space. It's just minimal. Okay? Come on, you can do it. Okay. If there was air resistance and we ignored it, objects will fall at the same rate no matter what their mass is. A feather and a bowling ball would reach ground at the same time. Way. Yeah, totally. Showed you that video. I will in a second. Okay? So having bowling ball and a marble, but this is a feather. Okay? Acceleration is still a vector quantity. And gravity, 9.81 meters per second squared, works towards the center of the mass. And for us, the center of our mass is Earth. So it works towards the center of Earth. So when we're falling towards the center of Earth, we're falling down. What have we learned to date about down? What direction is that? Positive or negative? Negative, except for when you're gravity. Gravity falls towards the center of Earth. Gravity is positive in the downward direction. I know, it's mind-bending, but it is. Okay? If we were working in the opposite direction, going up, gravity would be negative because gravity always works towards the center of an object. Okay? Terminal velocity is as fast as the velocity can go of that object right before the moment of impact. That's as fast as that object is going to go, the millisecond before impact. Let's look at some diagrams. There's 3 in this space. All right, here's my object. Right now, this object is at rest. What do I say about my velocity? If this is at rest, it's at 0 meters per second. Okay? In position B, so now I'm holding a rubber bouncy ball and I just let it go. It has a little bit of velocity. Okay? In step 3, this is right before impact. So right before impact, it's got a very long vector arrow. So vector arrows can describe to us the quantity of something. And not by a specific number, but by this is just starting, this is not moving, or this is like majorly in motion. Okay? So this is if I drop an object. Now, this is like this Bob Ross picture here. Here's my building. And here's my guy who's as big as the building, and he's dropping a ball. That's what this, yeah. Okay, he's dropping a ball off the side of the building. This picture here, an object being thrown up, is my guy with his baseball glove on, and he's throwing his ball up. Now we're not worried about an arc. It's up and it's straight back down. You can't see my second picture? That's okay. Bob Ross, all the way. Okay. Here it's in his hand, and he's getting ready to throw it out to outfield. Okay, this is A. It's the reverse. This is going to have a much larger velocity than in mid-toss. Why would you have more velocity when you first throw it than as it's towards the end of its jaunt? Sorry, I went out this way, but I mean up. If I take the ball and I toss it up, why is my velocity bigger right at the initial toss up than it is halfway up through the toss? Because why? Why do you think? CJ's not wrong. Let's help him out. Because gravity is pushing down on the ball. Okay? Here at the peak, what do we think? At the peak, let's be more scientific. Let's call them maximum height. Right before it starts falling down. If we could like snapshot it, it went as high as it absolutely could, and then it starts coming back down. What do you think its velocity is? Zero. Okay. Now it's coming back down. Is my vector arrow going to be smaller, equal than, or greater than the arrow at the midpoint going up? CJ thinks less than. Oh, I thought that's what you said.
You said it's probably equal.
Probably equal. Well, look at you, Cedric. You're on a path to passing physics. It is equal to. And then again, we have terminal velocity coming down. So we're going to have a much larger arrow, equal to, these two will be equal, but larger than the midpoint. So we could say that, let's look though. Gravity works in which direction? Towards the center of Earth for us. So what would we say about our velocity? Velocity is directional. What would we say about our velocity here versus our velocity here? A is positive. Why are you saying that? What would we say about the velocity here then? It's negative. But they're equal. What about this point here? Let's call this B1 and B2. VB1 is going to be equal to negative VB2 because they're at the same height. This is at same height. We called this BC, but let's call this E, just so we differentiate between this E and that C. Okay, that's all we're doing. We're just changing the letters so we're not confusing the maximum height velocity versus the terminal velocity. CJ.
For the guy on top of the building, can you draw like a guy at the bottom of the building so you do it?
No, he dropped a ball. All right. So this is what we can say here. The vector arrow would always be the same length. Okay, vector arrow would always point down with the same length at all locations on our path, on our trip down. Dropped is indicative of free fall. So then if I had to pick out the important pieces of information, really give me one piece of information. Okay, Aiden, another piece of information. Trying to find the height of the shelf. Okay, now we're going to start getting trickier. Princess, another piece of information. Okay, Joyce, still yet again, another piece of information. Remember, we've identified that this is free fall. So free fall tells us some very important things. We need to go back to Rayleigh. Rayleigh, what kind of velocity do you have? Nope, not unit. Do I have initial or do I have final? Final. So when I looked at drop, Joyce, what can I say about my initial velocity? 0. Okay, so see, we got 2 pieces of information out of that question from the word dropped. So we got to start like hunting for questions. And I wrote down height, but I'm going to change it to distance. Okay, now I have VF, I have D, I have G, I have VI. What formula do you think I would use to solve for the height? Remember, there's 5 that we know plus 1 that we had to memorize, but we really don't have to memorize it because we have it unexpanded. I have VF, VI, and G being what? G is also known as A, right? Good job. VF squared is equal to VI squared plus 2AD. I want to isolate D. That's what I want. Now, let's make this math really easy for ourselves. VI is what? 0. So that's going to be 0. 0 squared is 0. So when we simplify the formula, VF squared is equal to 2AD. Again, I want to isolate for D. How do I do that? Who's next on the list? Daniel's next on the list. Divide by 2A. So VF squared divided by 2A is going to give me my distance or my height. And then all we're going to do is we're going to plug our numbers in. So CJ is going to calculate and Paulina is going to fact check. What'd you get? Okay. Make sure when you're putting it in brackets and if you're trying to do it all in one shot, you go 11.7 x squared divided by bracket 2 times A times D end bracket. Otherwise, your equation will go 11.7 squared divided by 2, and then it will multiply all that.
I had like 700 before.
Yep.
6.977.
You got the same thing? Perfect. 6.977 meters. Let's look at our units. If I'm taking my velocity and I'm squaring it, I get meters squared per second squared. And then here I have meters per second squared. So when I look at my units, these are going to cancel out, and this is going to take this out, and I'm going to be left with a meter. So when we look at unit analysis, which is huge, huge. You can solve all things. You don't even need to memorize a formula if you can understand how the units work. Okay? Now let's go back to the problem, Avery. And how many significant digits do I have? Nope, only the numbers in the actual problem. Then 3. 1, 2, 3, 7 is going to have an influence there. So my height of my building is 6.98 meters. Okay. So when I look at these pieces of information that I have, what are we looking for, Kyle? Nope. What does it say? What is the maximum height? Okay. So maximum height is listed as D. Okay, so I have D, VF, T, and G, which we know to be acceleration. So don't get lost in trying to find a formula. It's our A. What formula would we pick, do you think, Joyce? If you look on your data sheet, you have all of those pieces. Do we have VI in our list of goodies here? No. We have A, T, VF, and D. Square. Yep, good choice. Okay, VF is what? I know, yeah, but what's the value? Sorry. 0. So this whole piece right here is going to be 0. Because anything multiplied by 0 is 0. So D is equal to negative 1/2 AT squared. All right, now we're going to plug in the numbers. So don't forget, we put this piece here in front of we put a negative sign. So make sure you carry it into your math. If you're going to make a mistake, you're going to forget to carry that negative sign. The other place that's very common to make a mistake is in the squaring. You'll forget to square it. Okay, so Princess is going to calculate it, and CJ is going to fact check it. What'd you get, CJ?
12.55.
Perfect. Daniel, when we look at the question, how many significant digits are we looking at? 3. 1, 2, 3. Which means that 5 is going to influence the first 5. And so my answer is going to be 12.6 meters. When we go back to the question and it's asking us maximum height, is that scalar or vector, Paulina? Do you think? Think it's vector? Do we need to? Yeah, we don't need to know the direction. It's just the height that the ball is going up to. So it's a scalar value. Okay? All right. Last one. This is the extension. So we have this problem here. I'm going to leave it on the bottom of the screen for now. All right. What is the velocity of the stone when it's released by the thrower? Velocity is vector, and we're going to look at two different ways to solve this. Both work consistently, so you can pick whichever way resonates in your brain better. Okay? Method 1, let's look at it. It says, what is the velocity of the stone when it's released by the thrower? Well, in the first question, here's our ball. They threw it up to maximum height. Okay? VF is 0 meters per second when time is 1/2. Right? We said that. We said it's 1.6 seconds to get the ball up to maximum height. VI starts down here. So if we were to list our knowns, what do you think one piece would be, Avery? Don't forget we have this question here, right? So which, sorry? Maximum height. Okay, we calculated that. So the more that we can stay away from something that we calculated, the more or the less error we introduce. So we'll hold on to that thought. Perfect. 0 meters per second. Kyle, what is time halfway? 1.6 seconds. And Cameron, what's another piece of information that we have to pull out of this question? Perfect. Gravity is going to be what? Negative 9.81 meters per second squared. Why are you saying negative? Because we're throwing the ball up. Perfect. All right. Now, based on those pieces of information, remember gravity is also known as A. We have A, VF. We are looking for VI. And we have T. What formula could we pick? Back to you, Joyce. Okay, divided by T. Now, VF is 0. So we have A is equal to negative VI over T. And we need to isolate VI. What are we going to take over? How are we going to move this to get VI, not negative VI, but VI? What are we going to do, Princess? Yep. So we're going to get AT, and we're going to pull the negative over here. We're just going to take the negative 1 over T and pull it over to the other side. We're going to take the negative with it. This way, when we get our answer, we know what we're understanding. If we get the negative VI, then we have to think about, like, say we get negative 0.6 and our answer, and we look for a negative VI, then we have to think, is that now becoming a positive? This way, if we can keep what we're solving positive all the time, if we get a negative answer, we understand what that negative means. Okay? So then we're just going to go negative times negative 0.81 times 1.6 is equal to VI. CJ, you're going to calculate, and Daniel's going to fact check. Kyle. Yep. You have no calculator. Okay, what'd you get?
50.696.
Meters per second. And when we look back at the question, CJ, how many sig digs can I go? We have to go all the way back to the original question where we have a number. 3. Nope, the other way around. The 9 affects the 6. Yeah. So VI is equal to 15.7 meters per second. It's a vector. So what would you say? Positive. Up. Up. Up is perfectly fine. Yeah. It doesn't tell us south or north. It just tells us that they threw the ball up. So we're just going to take their words.
7 meters vertically up.
Meters per second. Up. Yep. Okay, let's look at method 2. Now, method 2 takes a little bit of... Why would I need 3. So like say 1.57 times 10 to the 1. You can if you want. That's not wrong. But I don't have to. And the less times I have to move things around, the less error I introduce. My 3 sig digs, like when I look at my 3 sig digs, 15.7 is still valid. It's not like if, say, the answer was 280 and I could only do 2 sig digs, right? That would be the 2 and the 8. 28 is not representative of 280. So at that point, I would go 2.8 times 10 to the power of 2 to let me know that that 2.8 is multiplied by 100. But right now, I don't need to do that because the 15.7 is representative of the 15 that's there. Does that make sense? Okay. You wouldn't be wrong. If you put it in scientific notation, you wouldn't lose marks because you wouldn't be wrong. Okay, this one involves some algebra. So this is going to be an extension of your brain, and you are more than capable of doing it. Method 2 looks at the whole picture. The ball goes up, ball comes down. Sounds like a Kenny Rogers song. Okay? This is VI here, and this over here is VF. And when we go back in our notes for free fall object, which is right here, what did we say here at this point? That they're equal to each other. One is a positive and one is a negative. So at this point here, VI, which is going up, is equal to VF, which is coming down. VI is equal to negative VF. Okay? We have to all understand this piece. Are we all there? Thumbs up. I need a thumbs up at this point. If you're thumb sideways, let's figure that piece out. Thumbs up? Okay. So we're looking for VI equals 0. VF, now pay attention. My VF that I just wrote here is positive. My VF up here would be equal to negative VI, right? Positive VI is equal to negative VF, which is the same as saying VF is equal to negative VI. I got one nod of the head. Kyle got it? Daniel, do you see it? Okay, right here, my VI is when I'm throwing the ball up, right? So it's positive. When it comes down, my final velocity is negative. Okay? Now when I don't look at the picture and I just look at the math, okay? VI being equal to negative VF is the same as VF being equal to negative VI. Do you see that? I'm not asking you to change a concept. I'm just asking you to see the math part of it. Here, because up for velocity is a positive direction, not gravity velocity, okay? Do we see the math piece? No, we're not looking at numbers. I just need you to understand that when I say VI is negative VF, according to the concept, mathematically it's the same as saying VF is equal to negative VI. Okay, that's all I'm asking you at this point. Do you see that piece? Okay. So then here, my VF is equal to negative VI. Oh, I didn't put a 0 there. I meant to put a question mark. That could be what's confusing everyone. We're looking for VI. Sorry. We're looking for VI. Okay. Acceleration, still negative 0.81 meters per second squared because it's still going up from VI. And my time, though, is now this piece here. And time was equal to 3.20 seconds. Okay? We agreed to this piece of information once I made my mistake, corrected my mistake? Okay. Looking at VI, VF, acceleration, and time, Paulina, what formula would you pick? Would I pick the same one that we used? Yeah. It had all the same pieces, right? It has A, it has VF, it has VI, and it has T. Okay. This method too is looking at it from strictly this question here and not going back to knowing what our VF final is. We knew VF final is 0 at maximum height, right? But remember I said when the ball comes down, right before it lands in the catcher's mitt, it's going as fast as it can go. So we don't actually have a VF coming back down. We have a VF at maximum height. We know that's 0. We don't have the VF right before it stops moving. Okay? So this is where the algebra comes in. A is equal to, what did we say VF could be equal to? Negative VI minus VI all over T, which looks like A, what? I'll stop. All I did, Avery, was I did a substitution. For this VF here, I put in this piece here. Okay? Because we don't actually know what VF is. So then A is equal to negative 2VI over T. right? When you add two like terms together. Yeah, that's that algebra piece. Okay. Now I can solve for VI, and I would get AT. What do I do with my 2? Divide by. I'm going to bring the negative sign with it so that I leave my VI positive. That's all I've done. I've just grabbed that negative and brought it with it. Okay? What? So here, I'm just rearranging my formula. How do I move T out of the denominator? VI, negative VI minus VI gives me negative 2VI. I just added two like terms together. Right? X plus X is 2X. You good? Okay. Do you see how the negative 2 moves over? You just didn't know where the 2 came from. Okay, perfect. All right, so now I can solve. So I'm going to go negative 9.81 meters per second squared multiplied by 3.20 seconds and divide it all by 2. So Kyle, what do I get for an answer? Oh, sorry, I forgot to put my negative down there. See? Told you if you're going to forget something, you're going to forget to move a negative. So 15.696 meters per second. I'm going to go back to the original question where we got 3.20 from. Again, it's 3 significant digits. So VI is 15.7 meters per second up. And it's the same answer because all we did was we figured out half the time here and we left the time whole here and then divided everything by 2. So it's 2 ways to look at the problem, and it's whatever way your brain understands it the best. Okay? You understand this one the best? Method 1? Yeah. You just need to remember in method 1, your downfall will be in remembering to divide the time in half. That's where an error will get made. Okay? Let's start. We've got 10 minutes. Let's start on these questions. 25, 26, 30. Those are the acceptable. Those are like Mrs. Johnson's straight aheads. Let's start on those 3. See how many we can get done of those 3 in 10 minutes.